Alright, so hi guys. This is basically going to be a sort of walkthrough of some code that I wrote, kind of like a baseline model for competition 5. This is the competition where we have to determine whether a lyric is pop or rap. So right off the bat, we just import a couple of libraries that we're going to be using. Most importantly, TensorFlow and these parts of TensorFlow, namely Tokenizer and pad sequences. I'll talk about what these are very soon. These are just some parameters that we define. We'll keep coming back to them throughout this video. This code is, I was working off of Google Colab, which is a form of, it's offered by Google, and I uploaded all the kind of training and testing files, the CSV files from Kaggle onto my home Google Drive. And so this basically connects your Google Colab runtime to your Google Drive, right? So if you have any files stored, then you can just use them in your Google Colab. It'll ask you for this authentication code, and you just have to go to this link, and then it'll generate it for you. That's fine. So once we have that, I already ran all this stuff, so that's why I don't really care that the runtime is over. I'm just walking through what already has been run. So when we print this data frame, we get all this stuff, and so this data frame is just an object. It's basically just a two-dimensional matrix that offers a few, that has a few tricks up its sleeve. So we have a lyric and we have a class, right? And so 1 here represents pop and 0 represents rap. And you can see some of the lyrics that we have over here. And so the next thing is to basically split things into training and validation sets. So we're basically first going to create a NumPy array of the lyrics and the labels. I just did some counting here to see, okay, how many lyrics do we have, how many are pop, and how many are rap, and then we just split all of these, arrays into training and validation. So in most machine learning tasks, usually you don't want to just solely measure your performance, your model's performance using your training data set, because usually you'll have some sort of overfitting on a data set where your model will almost sort of memorize your training data set but doesn't actually generalize to other sorts of data sets, which is the end goal of the machine learning task anyway. So in order to make sure that you're not overfitting or reduce the degree of overfitting, you usually use a validation set. So our training size, or the size that I used, was pretty large, like 49,000, and there's only 51,000 lyrics in the whole set, so we're only using about 2,000 for validation. I think that's okay given the size. If you guys are able to get better results with something else, then just let us know. Yeah, so now we're actually getting to like the meat of this code. The Tokenizer object is basically a way that TensorFlow provides that maps words to numbers, right? When you pass data into a neural network, you have to represent it numerically. You can't pass in like strings. So what a tokenizer does is it'll take some body of text that we have, and here we pass in training lyrics, which is just a NumPy array of all the lyrics that we have in our training set. And then it'll generate, if you get this word index thing from the tokenizer, word index is basically a dictionary where the keys of the dictionary are words, and then the values of the dictionaries are just arbitrary numbers. Except they're not arbitrary, they're sorted according to the frequency of these words in your corpus, in your training corpus, right? So as you can see, I'll talk about what this means very soon, but the most common word in our corpus was I, and the second most common word was you, and the third was the, right? And so it just basically assigns these numbers to this, to every single word, so that when we are training and testing, we can represent data numerically instead of, strings. So the next part is basically once we have this word index and tokenizer object, we can call this function text to sequences. And so our our training lyrics before, as you can see, like they were just a list, and the elements of this list were just all of this stuff, right? So the first element would be the text can't drink without thinking about you, right? And then the second element would be this, and the third element would be this. And so we want to convert that to numbers. So this method, text to sequences, will basically convert a training lyric into a set of numbers that we can pass into our neural network, right? And so here I've printed out the training sequence after it gets converted, right? So this actually corresponds to the first lyric that we have up here. So, just the lyric is can't drink without thinking about you. And you can see that this is actually the same length, right? Can't drink without thinking about you. And each of these numbers actually corresponds to, one of the words in the lyric. So the last word was you, and as you can see, you maps to 3. So that's basically how it works. It just converts each word into a number. And then we also pad it, right? So when we're training neural networks, especially with like optimized code like Keras or TensorFlow, we want all the elements of a batch to be the same length to take advantage of optimizations that come from GPUs. So padding just makes all the elements of your training set the same length, or at least all the elements of your batch the same length. So I haven't shown that here. I didn't print it out, but basically, if the length of if the length that we set, if this is shorter than the length that we set, then it would just add a bunch of zeros, and then if it was longer than the length that we set, it would truncate them. And so that's basically what that means. So we basically standardize the length. And now this is the actual model that does the cool part. I'm not going to talk about the LSTM network here. That's like a whole lecture that we could talk about that. But I will talk about this thing called the embedding. So the embedding is basically a matrix. In our case, it's size 4,000 by 4,000 by 16, right? So each of the rows in the matrix corresponds to one of the words in this dictionary. And so basically, once we get a list of numbers like this, it'll convert each of these numbers into a vector representation, right? So each of these represents a word. So basically, it's the embedding converts each of these numbers into a vector representation of the words. And so you can imagine, over time, if the goal of this is to, predict if a song is pop or rap, then the ideal thing for the embedding to do is to somehow learn to represent the meaning of each of the words, so that when we're actually doing classification, the rest of the model can use those vectors that somehow capture the meaning to solve the task, right? Because you can't, you need to know the meaning of the word somehow in order to judge if a lyric is pop or rap. So this is what this does. It basically generates vector representations of each word, and then once you pass in like this sort of array here into the model, it'll kind of mash all of those vectors together and then pass that on to your LSTM. And then the LSTM just is connected to a dense layer, which is just your regular neural network. I added a bit of regularization here. As we'll see shortly, we still are overfitting a bit, but that kind of reduced it slightly. And then the last layer here is a dense layer, just of output size, just one output node. And and the loss function is binary cross entropy because the classification labels are 0 or 1, and yeah, that's it. That's notable. We have about 208,000 trainable parameters. This is the kind of output that I got from training. Before training, I just converted everything to a NumPy array because it wouldn't work without that. I think, um, yeah. And then, these are the graphs that we generated from training. So as you can see, there is a bit of overfitting, right? The orange lines in both of these graphs represent the validation, and then the blue lines represent the accuracy. So you can see the accuracy is like on the upward trend, and here for loss is on a downward trend, which is good. But the validation accuracy has an overall decrease, and the loss has an overall increase. And both of these are really small deviations. Here it started off 87% accuracy, and here it's about 85. So it's not a huge, thing. But definitely, if this was going to be your submission, rather than just sort of like a baseline demo, you definitely want to maybe try some more dropout, mess with the hyperparameters of your model, and try to first prevent overfitting, and then see if you can actually improve the performance a bit. So once you have your model trained, usually you want to save it, right? If you want to train again, you don't want to have to like restart, especially if you took a long time. Oh, and just a tip, if you don't already know, when you're training, you can take advantage of Google provides free compute resources, so you can actually. I was previously on a GPU. You don't need to use anything if you want. You can just run it without any accelerator, but you can also get a GPU or even a TPU, which is even more optimized for deep learning computation for free. Like Google offers these for free. So yeah, take advantage of it. And so now we're just, this is kind of outputting the submission file, right? So this is also stored on the home folder of my Google Drive. If it's in a different folder on your Google Drive, you probably want to change this address a bit accordingly. But yeah, so this data frame, it's going to be the same thing as before, right? We basically get all the lyrics, convert them according to the tokenizer, pad them. These two lines just, the outputs of the neural network are like decimal numbers, because so all this does is anything that's higher than 0.5 that the model outputted, it'll convert it to 1, otherwise it'll convert it to 0, right? So Kaggle only, for this competition at least, Kaggle will only accept like integers, so this solves that problem, right? And then basically I just kind of did it like this so that it makes it easier to submit. I just put in all of these labels into this data frame object. That's what this line does. And so you can see, this is the final result of our model. These are the lyrics, and this is the output that it came up with. This model on the Kaggle public and private leaderboards got about 82%. So it's I think there's definitely a room to improve on this, especially because of what we saw here, right? And it's not even that big of a model. I think we could probably have experimented with some more things, played with some more hyperparameters. This is just a baseline to get you started. Yeah, and then this is just writing to a submission.csv file. And so that's that. That's basically everything that we need for the Kaggle submission. But I think there's also something a bit more interesting that you may not know about, even if you were able to solve the competition yourself and get a pretty decent score. This is something that you can do that's pretty interesting, right? So first, this block of code basically gets the weights from the embedding, and so you can see, as I mentioned before, the embedding matrix has a size of 4,000 by 16. So each row in this matrix corresponds to one of the words in our tokenizer word index object, and then each row is a vector representation that somehow captures the meaning of that word, right? And so before moving on, I just created this reverse word index. So the previous word index, the keys are the words and the values are the numbers. So this one, instead, the values are the numbers. I mean, the keys are the numbers and the words are the values. Hopefully I got that right. And I'll show you what exactly this does. But this basically creates two files. Out_v is a file that contains all the vectors generated from our embeddings, and out_m contains all of the actual words of our embeddings, right? And once we save these, we can actually go to this website. I already loaded everything here. In order to load, you basically press this. You load your vector file here. Load your metadata file, or just, these are just the text, the word text. You just load that here, right? That was the, going back to the, that was, so out_v here was the vector file, and out_m was your metadata file that contains the actual words. And so once you do this, you can press load, right? And then you press sphereize data. And you can actually see a sort of 3D visualization of the embeddings that your model came up with, right? So it's super cool, right? It was able to, this basically condenses all of the information in your 16-dimensional vectors using a technique known as principal component analysis into a space that you can visualize. And you can rotate this around. You can actually see certain words, right? So yeah, so you can basically like see the meaning of different words. Like, for example, if I search up like beef, like wrapped beef, that's more on this side. You search up like caring, that's more on this side. These are both like two cherry-picked examples. Not all of the words are going to be like that, but it's kind of cool to visualize things. There's also